Most people walk past a flash of shimmer in creek gravel without a second glance, mistaking it for a sunlit fleck of mica or wet quartz. But under the right conditions, that subtle glint can betray the presence of minerals linked directly to diamond-bearing deposits, indicators that signal a geologic signature far more valuable than they appear at first glance. The problem is one of expectation. When people think of diamonds, they imagine finished stones, flawless, cut, and brilliant. But in the wild, diamonds rarely announce themselves so boldly. Rough diamonds often resemble slightly greasy, translucent pebbles, duller than quartz but with a unique internal light. Their presence is almost always telegraphed by a supporting cast of heavier, darker minerals that concentrate in precisely the same places. If you know what to look for, the glimmer in gravel can be a coded message from deep time. This first clue tends to show up in ancient stream beds, paleochannels, where heavy minerals settle over millennia. Unlike gold, which accumulates in obvious traps and cracks, diamond indicator minerals are dense enough to resist high flows but light enough to travel modest distances from their volcanic source. A telltale sparkle might emerge where high-energy water once slowed. The inside bend of a dried river arc, a back eddy in a modern stream, or the base of a slope feeding sediment into a low-lying zone. These shimmer points are neither random nor rare, but they demand close scrutiny and the right tools. From the surface, a promising patch may look like nothing, brown gravels with occasional dark grains or slightly glassy fragments. But under oblique sunlight or angled headlamp inspection, individual grains of pyrope garnet or chromite can catch the eye. They flash differently than mica, not flaky, but solid, almost metallic. Some will be magnetic. Some will sink aggressively when panned. A few may cling together in your sluice's final trap, too heavy to flush. All of these are potential breadcrumbs pointing to a kimberlite or lamprite source, and just possibly diamonds. A glimmer alone is not a diagnosis, but certain traits in a raw crystal's appearance can instantly raise or lower suspicion. Most of the Earth's surface stones scatter light in a dull, diffuse way. But diamonds, even in the rough, exhibit adamantine luster, a sharp, almost oily brilliance that seems to glow from within. It's subtle in poor light, but unmistakable when you train your eye to distinguish between mere shininess and optical density. The key is angle and motion. Field collectors often learn to rotate stones slowly under directional light, watching not for brightness alone, but for how that brightness behaves. Quartz, for instance, produces a vitreous luster, clean but shallow. Glass fakes scatter too broadly and lack internal reflection. True diamond candidates reflect light with a tighter, more directional shimmer. When slightly wet, they don't gleam like polished metal. They pulse, especially if their surface is smooth and free of pitting. Another tell is shape. While most diamonds found in the field are broken fragments, some preserve partial or full octahedral habit. These forms often appear as distorted pyramids or twin structures, with flat faces meeting at precise angles, something quartz rarely forms without additional terminations. Even when rounded by erosion, remnants of octahedral planes can remain readable under magnification or touch. If you feel sharp edges that resist wear, that's another data point. Color is a poor diagnostic tool early on. Natural diamonds can appear colorless, yellowish, brown, gray, even green from surface radiation. A clearer signal comes from transparency. A promising rough may appear cloudy on the outside but show depth inside, especially when rotated against a dark background. Many candidates exhibit what field geologists call greasy glass optics. Not quite transparent, not opaque, but oddly penetrable to light. Even the sharpest eye won't help if you're looking in the wrong place. Diamonds don't form just anywhere, and more importantly, they don't travel far. Understanding the geologic context is critical. The majority of Earth's natural diamonds originate deep in the mantle and reach the surface via explosive volcanic eruptions through kimberlite or lamprite pipes. These narrow, carrot-shaped conduits are often long eroded and buried, but they leave mineralogical fingerprints in downstream sediments. Terrain logic begins with tectonics. Diamonds form under high pressure and temperature, conditions found beneath ancient continental cratons, where the lithosphere is thick and stable. These cratons, like the Kopval, southern Africa, Slave, Canada, and Siberian shields, are the known parents of major diamond fields. Any terrain without a similar deep-rooted stability can likely be ruled out, no matter how promising the surface indicators seem. However, even within favorable cratons, pipes are sparse. That's where erosion patterns matter. A kimberlite pipe formed 90 million years ago might have been weathered down and buried under alluvium, with its diamonds washing into nearby drainage systems over geologic time. The goal is to reverse engineer this sediment transport, reading the land like a slow-motion crime scene. Look for paleochannels, ancient riverbeds now stranded above current water flow or infilled with coarser material. These often appear as subtle depressions or alignments in satellite imagery, particularly in arid or semi-arid zones. Gravel fans spilling from hills into plains are prime zones, especially where you see a mix of heavy minerals deposited in apparent layers. Local topography refines the search. Diamonds, due to their hardness and hydrophobicity, behave differently in water than gold or sapphires. They can roll farther, resist grinding, and often lodge in quiet zones downstream of turbulence. Creek-inside bends, eddy pools, and the downstream side of obstructions like boulders or roots are common trap points. Equally important is looking uphill. If your concentrate includes multiple indicator minerals, trace the likely uphill catchment for signs of weathered pipe material. Lamprite deposits, like those that produce the Argyle pink diamonds in Western Australia, offer a different terrain signature. These pipes form in tectonically active margins rather than cratonic cores, and their surface rock is often richer in feldspar, serpentine, and mica. Knowing whether you're in a kimberlite or lamprite terrain changes what indicators you seek, and how you interpret the gravel you gather. Another overlooked signal is vegetation. In some regions, the magnesium-rich soils around decomposed kimberlite or lamprite alter the flora. Stunted or specialized plant growth over circular soil patterns may mark a long-buried pipe. Early De Beers explorers in South Africa used aerial plant mapping as one of several reconnaissance tools. Permits and access are a final terrain factor. Many promising zones are on private or restricted land, including tribal territories, mining claims, or protected ecological zones. Sampling without proper permissions risks not only legal trouble, but the invalidation of any future claims. Always verify land status through regional mineral rights registries before sampling. Long before a diamond ever appears in your pan, its trail is marked by more cooperative allies. These are the indicator minerals, dense, erosion-resistant fragments that travel alongside diamonds from their volcanic source and survive in stream gravels. Spotting them reliably is the first true threshold between speculative and strategic search. And while they might lack the flash of a gem, they're often far easier to find. The key indicators in diamond prospecting are pyrope garnet, chromite, ilmenite, and to a lesser extent magnetite. Each one originates within the same deep mantle conditions as diamonds and is carried to the surface by the same eruptive events. Their chemical compositions and physical traits vary slightly depending on whether the source rock is kimberlite or lamprite, but their collective presence in a sediment sample raises the probability of nearby diamond-bearing material. Pyrope garnet is the most famous. Typically purplish red to deep violet, its small crystals, often under 2, stand out in a black sand concentrate due to their translucency and rounded edges. Unlike almandine or spessartine garnets common in metamorphic terrains, diamond-associated pyropes often have a distinctive chrome-rich chemistry and form in high-pressure conditions. Field indicators include a vitreous luster, and under magnification, a lack of surface pitting. In cross-polarized light, lab analysis reveals a magnesium to chromium ratio that tightens the diamond potential. Chromite is another heavyweight. Opaque and black with a slightly greasy luster, it's sometimes confused with magnetite or hematite, but unlike those, it's not magnetic. Its specific gravity (4, 5, 4, 8) makes it one of the first minerals to sink in a pan. Rounded, submetallic grains found alongside pyrope in a drain are a red flag worth pursuing, especially if clustered. Ilmenite, typically a dull black or dark gray, is moderately magnetic and slightly more challenging to distinguish. It often carries trace titanium and appears tabular or angular. A quick magnet sweep of your concentrate can separate out magnetic grains. If they respond weakly but are still dense, you may be handling ilmenite. Cross-confirmation with hand lens inspection of luster and grain shape helps narrow the ID. Magnetite itself isn't diagnostic but supports the suite. It's common in many terrains, so finding it alone isn't significant, but finding it with chromite and garnet sharpens the profile. Other associated minerals include clinopyroxene and spinel, especially in less weathered kimberlite float material. The goal at this stage isn't proof, it's pattern. A single garnet could be an orphan, dropped by ancient flows or unrelated metamorphic events. But 5 or 6 indicators appearing together, in a tight grid across a few hundred meters of terrain, shift the odds. Especially if they show rounding, suggesting travel, concentration, suggesting settling, and mineral variety, suggesting a pipe source. A pan full of heavies can stir excitement, but unless you separate the true signal from the background clutter, it may all lead to false hope. That's where the magnet sweep and density field tests come in. Simple, fast, and surprisingly revealing steps that begin to divide the real mantle-derived indicators from the noise of everyday erosion debris. Begin with the magnet test. A basic neodymium magnet, preferably encased in plastic or duct tape to prevent contamination, is sufficient. Slowly pass it just above your dried concentrate spread on a white plastic plate or sturdy card. You're watching for 2 behaviors: strong attraction and rolling drift. Strong pull with a jump suggests magnetite. Weak movement, especially in tabular or angular grains, hints at ilmenite. If grains neither move nor twitch, they're likely non-magnetic, critical for narrowing down to chromite or pyrope. Remove all strongly magnetic material and reinspect the remainder. Often, once magnetite and magnetic ilmenite are gone, subtler grains become visible. Pyrope garnet, for instance, may appear as rounded, wine-red or purplish grains that didn't react to the magnet but feel notably dense when moved between fingers or tapped into a vial. In the field, the moment you sweep a long-wave UV flashlight over a cleaned concentrate and see a pale blue or green glow in one of the grains, your pulse may quicken, but it shouldn't yet convince. Fluorescence under UV light, especially in long-wave, 365 nm, is one of the earliest non-destructive hints that a candidate stone might be a diamond. However, the signal is murky, helpful but not definitive, because other minerals and even synthetic fakes can fluoresce as well. Most natural diamonds fluoresce under UV, typically blue, but sometimes yellow, orange, or green depending on their nitrogen content and structural defects. The classic reaction is a soft, hazy blue that appears strongest in type Ia diamonds and certain stones from Canadian or African cratons. Yet many real diamonds show no fluorescence at all. Worse still, many simulants like some zircon, calcite, synthetic spinel, and even plastic can emit similar glows under UV. So what's the test logic? Start by ensuring a controlled environment, total darkness, long-wave UV only not shortwave, and a clean, dry sample. Isolate your most promising grains, non-magnetic, high luster, possibly octahedral or unusually heavy. Expose them at 1–2 inches distance for 5–10 seconds. Note not just color, but intensity, evenness, and whether the glow lingers phosphorescence. Diamonds rarely show phosphorescence, while some synthetics and calcite do. A bright green or white glow that fades slowly, probably not a diamond. If UV gives you a maybe, the next test is thermal conductivity. Diamonds conduct heat extremely well, one of the best among nonmetals, whereas most fakes do not. In the field, this test requires a portable thermal conductivity meter, a diamond tester, which uses a heated probe to measure how quickly the stone dissipates heat. If your sample is large enough, over ~1, dry and clean, you can apply the probe and get a reading in seconds. A beep or green light suggests high conductivity. But there's a catch. Moissanite, a synthetic silicon carbide, also conducts heat and almost identically. Worse, it also shows adamantine luster, high hardness, and may even fluoresce. So the thermal test is only reliable when paired with another, electrical conductivity. Moissanite often conducts electricity, diamond does not. Some dual-mode testers include this check, Or you can improvise with a small multimeter and electrodes, though it's less precise. Together, these tests begin to triangulate your candidate. A grain that's non-magnetic heavy (3, 5Sg) shows pale blue UV fluorescence, conducts heat but not electricity, and resists scratching by CC sandpaper is strongly suspect. But even now, the field tests point only toward probability, not certainty. Many natural stones can pass 3 out of 4 tests and still not be diamonds. Others may fail one due to contamination or surface wear. That's why field testing should never be your final decision point. It's your filter. A grain that passes UV, thermal, and density checks should be flagged, bagged, and cataloged with exact GPS and context. Because once these suspects emerge, it's time to ask the harder question. How do you scale your process without chasing anomalies? By the time you've handled enough concentrates, seen enough UV flashes, and puzzled over enough borderline tests, you realize that finding a diamond isn't about luck, it's about execution. A consistent field workflow transforms scattered clues into actionable leads. It also helps you avoid the most costly error, chasing a single positive test while missing the broader signal in the surrounding terrain. The process begins with grid logic. Don't wander randomly. Define a sample grid across your target zone, typically 25 to 50 meters between nodes, depending on terrain and drainages. Each grid point becomes a sample site, marked with flagging tape or GPS-tagged stakes. Start from downstream or downslope positions and work inward and upward, following indicator mineral concentration. The goal is not to find the diamond at each site, but to observe how indicator density rises or falls. At each grid point, collect 10-15 liters of material from the top 10-20 cm of the pay layer. Avoid mixing layers. You want consistency across sites. Dry sieve through 20 and 40 mesh to isolate the 0, for 1 fraction, the sweet spot for most indicator minerals. Pan this fraction slowly. If you have access to a sluice or spiral concentrator, use it for larger batches to speed things up, but hand panning ensures you don't miss outliers. Your concentrate, typically 1.5 grams per pan, is then spread for inspection. Remove magnetic grains with a strong magnet. Bag these separately. Sometimes weakly magnetic ilmenite or altered chromite can still matter. The remaining non-magnetic fraction is your core sample. Examine with a 10x to 20x hand lens. Look for color, purplish red garnets, opaque black chromite. Shape rounded grains suggest travel, angular ones hint at nearby sources, and luster glassy for garnet, greasy for chromite. Record everything. Grid point, number of garnets, chromites, non-magnetic heavies, presence of UV-active grains, even subjective weight impressions. Use waterproof sample bags and logbooks or apps. Keep each sample separate and label. Once indicators begin to cluster in a grid, say 3+ grains per pan across 3 adjacent points, it's time to tighten the grid spacing or move upslope. This helps triangulate the source. Look for erosional features like gully heads, slope breaks, or soil color shifts. Kimberlite and lamprite pipes often alter surrounding soils. They may appear paler, greener, or richer in clay. When suspect stones appear, test in sequence: magnet sweep, UV exposure, thermal conductivity, and if possible, electrical conductivity. Label each grain that passes more than one test and bag it. Flag the site prominently. If a candidate stone passes all field tests, collect a larger bulk sample from that point for later lab analysis. The most important habit is to avoid overinterpreting single grains or anomalies. The workflow isn't about instant reward. It's about confidence through replication. That's what turns a maybe into a probable pipe source, and it's how professionals justify drilling or detailed trenching. The most deceptive mineral you're likely to encounter in the field isn't glass, quartz, or even synthetic spinel. It's zircon. Small, dense, often glassy and beautifully lustrous, zircon shows up in exactly the size range and terrain position where you'd expect diamond indicator grains to appear. Worse still, some zircons fluoresce, resist scratches, and even mimic the weight of a tiny rough diamond. For an untrained eye, it's the perfect trap, seductively promising, consistently misleading. Zircon's specific gravity typically ranges from 4.6 to 4.7, higher than diamond's 3.52 and well above quartz. That means in a pan or sluice, zircon drops fast and accumulates with your heaviest concentrate. It's often found as rounded grains in old streambeds and colluvial zones, appearing pale yellow, brown, or colorless. though pink and red variants are also common. These colorless or lightly tinted zircons are especially problematic because under angled light they flash like a gem. A good hand lens view may show sharp, glassy edges and a brilliance that rivals moissanite. When dry, zircon can show an almost fused glass texture, clean, rounded, but with high reflectivity. In the heat of a field survey, it's easy to think you've found something rare. Even worse, many zircons do fluoresce under long-wave UV, especially yellow or white specimens with low uranium content. They often emit a whitish or green-blue glow, similar to poorly formed diamonds or high-nitrogen stones from lamproitic sources. But zircon gives itself away under closer scrutiny. The most decisive field test: double refraction. Unlike diamond, which is singly refractive, zircon is strongly birefringent. When viewed under a 10x loupe, especially from the side or at an angle, the edges of zircon grains appear doubled. Facet lines seem to blur or echo slightly. This effect is subtle but visible even in sub-tomb grains, provided the surface is clean and the viewing angle shallow. You can also use polarized sunglasses or a small polarizing filter held over a light source. Place the zircon on a white card, rotate it, and watch for internal color fringes or doubling lines as you change the angle. A diamond or true indicator grain won't show this behavior. Zircon will. Another giveaway is hardness. Zircon ranks 6, 5, 7, 5 on the Mohs scale, harder than quartz but softer than diamond. If you have silicon carbide sandpaper around Mohs 9, you can rub a clean zircon grain gently and observe surface scratching. Diamond resists. Zircon dulls slightly. Under a loupe, look for abrasion patterns. Zircon's sharp edges wear down faster than those of true diamond or moissanite. Finally, zircon is common, abundantly so in certain terrains. If your pan yields dozens of colorless, dense, glassy grains in non-cratonic sediment, especially in volcanic or metamorphic regions, they're almost certainly zircon. Even in cratonic terrains, zircon's ubiquity in accessory minerals makes it a background presence, not a signal. The danger isn't in finding zircon, it's in chasing it. Every hour spent tracing a zircon-heavy gravel fan upstream is an hour not spent following true indicator minerals. The antidote is repeatability. If the grain fails birefringence or gets scratched, or if it clusters without garnet or ilmenite support, reclassify the site and move on. Your credibility and your time depends on resisting zircon's false promise. Just when your toolkit seems airtight, thermal tests, luster checks, UV, and refractive clues, along comes moissanite, the great deceiver. In the field, moissanite is the most dangerous false positive in diamond hunting because it passes nearly every quick diagnostic test. It conducts heat like diamond, matches its adamantine luster, exceeds quartz in hardness, and often exhibits no double refraction visible without specialized optics. In fact, it was first identified in meteorites before its synthetic twin flooded the gem market, complicating fieldwork for anyone chasing rough stones. Moissanite scores 9.25 on the Mohs scale, harder than corundum, nearly indiscernible from diamond in scratch tests. It conducts heat, just like a diamond, fooling basic thermal probes. It's doubly refractive, yes, but only subtly so, and in irregular fragments that aren't clean-cut. Facet doubling can be near impossible to see under a loupe. Add in its high specific gravity, (3), 2, and you have a near-perfect field mimic. To make matters worse, synthetic moissanite now circulates through secondary markets, old tailings, and even crushed gravel mixes imported for construction or landscaping. It's not common in natural sedimentary systems, but it does show up, especially in zones near old industrial dumping grounds or synthetic testing fields. Some lab-grown moissanite even exhibits controlled fluorescence, deliberately engineered to imitate diamond behavior under UV. So how do you beat it? The first critical test is electrical conductivity. Natural diamonds are insulating, zero electrical conductance. Moissanite, being semiconductive, will show measurable electrical response. A dual-mode gem tester, portable, field-ready units now standard among serious prospectors, can differentiate by switching between thermal and electrical modes. If your stone conducts both heat and electricity, it's not a diamond. If you lack a dual tester in the field, you can perform a crude conductivity test with a sensitive multimeter and foil strip electrodes, but this requires dry, clean stones and very stable contact. More reliably, retain suspect samples for lab testing. If a stone passes thermal, UV, and luster checks but shows ambiguous results visually, it must be tested under crossed polarizers or using advanced spectroscopy. Not a field solution, but essential for verification. Moissanite's behavior under crossed polarizing filters can also hint at its true identity. While a diamond remains dark under rotation, moissanite can flash light or show interference colors, especially when mounted on a light background. Try sandwiching the grain between two polarizing filters and rotate one. Any light flicker or glow suggests double refraction, strong evidence against natural diamond. Another clue is origin context. If your moissanite-like grain appears in terrain with zero supporting indicator minerals, no garnet, chromite, ilmenite, it's suspect. Diamonds almost never travel solo from pipe to pan. Moissanite, especially synthetic, can appear alone. If the terrain lacks kimberlite or lamprite textures, and no other supporting minerals are present, even the best-looking stone should be treated cautiously. There's a final irony here. While moissanite is often a disappointment for the diamond prospector, it's not valueless. High-quality natural moissanite is rare and has its own gem value. But synthetic moissanite, even when perfect, has flooded the market and fetches a fraction of a similar-sized diamond. The challenge is knowing when to continue testing and when to shift your focus back to more promising terrain. No matter how convincing your sample, how rich in garnet, how strong the thermal test, how intense the UV glow, none of it matters if the terrain itself can't support the diamond story. Diamonds require a very specific set of conditions to form and survive the journey to the surface. And while the indicators can be found globally, true diamond-bearing environments are geologically restricted. Knowing where the entire pipeline, from formation to erosion, makes sense is the difference between a credible claim and a geological mirage. Start with the basics, cratons. These are the ancient, stable cores of continents, often more than 2.5 billion years old. Their thick lithosphere, extending over 150 kilometers deep, provides the high-pressure, low-heat environment needed to form and preserve diamonds. These roots also allow explosive volcanism to carry diamonds upward without destroying them. In short, no craton, no confidence. Globally, 3 cratons dominate diamond exploration. Kopval Craton, Southern Africa, home to many of the world's richest diamond mines, including the Kimberley Pipes and Venetia. Slave Craton, Canada, hosted Ekati and Diavik, discovered through meticulous indicator mineral tracing in tundra conditions. Siberian Craton, Russia. Yakush's Mir and Yudichная pipes are among the deepest and most productive. Secondary cratons in Brazil, India, and parts of Western Australia, Yilgarn and Kimberley regions, also support diamond occurrences, but these are more weathered or disrupted, meaning indicators may be spread or eroded beyond easy identification. If your terrain falls outside a cratonic zone, you face steep odds. Most tectonically young areas, like the Andes, Himalayas, or Pacific volcanic arcs, may show garnet, chromite, or spinel due to metamorphic or igneous processes, but not the right chemistry, depth, or thermal profile for diamonds. Their indicators are mimics, not messengers. Even within cratons, you need the right host rock exposure. Kimberlite and lamprite pipes are narrow and easy to miss. They may be buried under laterite, overburden, or alluvium. In temperate zones, glaciation may have scattered material over vast distances. For example, indicator minerals in the Great Lakes region often appear hundreds of kilometers from their source, carried by Pleistocene ice flows. Where this method excels is stable terrains with known but unmapped pipes, especially where weathering has liberated diamonds and their indicators into drainages. Parts of the U.S. like Arkansas, Colorado, Montana, and Wyoming all have lamprate or kimberlitic potential, though often overlooked due to sparse commercial activity. In Canada, Alberta and Quebec offer underexplored cratonic zones. In Africa, Tanzania and Angola remain frontier zones despite known deposits. Terrain failure is equally diagnostic. If you're sampling in river valleys underlain by recent volcanic basalts, marine sedimentary basins, or metamorphic schists without associated peridotite or pyroxenite intrusions, diamond probability drops sharply, even if your pan looks rich. Indicator minerals may be present, but they belong to different formation stories. Misreading them is a common mistake. Even when diamonds themselves are elusive, their conduits leave marks too distinct to ignore. Kimberlite and lamprate pipes, the volcanic structures that deliver diamonds from the mantle to the surface, carry not only indicator minerals, but host rock fragments and textures that, once understood, transform blind searching into informed targeting. Knowing how to identify kimberlite or lamprate in the field, even in its weathered form, is among the most powerful skills a prospector can develop. Kimberlite, the more common of the two, typically presents as a fine-grained, ultramafic igneous rock, rich in magnesium, iron, and volatile components. In fresh exposures, it appears dark green to blue-gray with a speckled texture, formed by a matrix of serpentinized olivine and scattered macrocrysts of garnet, ilmenite, and chromite. But in most field scenarios, you won't find fresh kimberlite. What you'll see is its deeply weathered form, soft, yellowish-green or brownish clay-like material, often sticky and prone to swelling when wet. To spot this in the wild, focus on soil anomalies. Kimberlite weathers faster than surrounding country rock, often creating circular depressions or donut-shaped ridges. Soils above pipes are typically more fertile, thanks to the high magnesium and potassium content, and may support distinctive vegetation, stunted growth in some regions, or lush weeds in others, depending on local ecology. One diagnostic clue is blue ground, a compact, blue-gray decomposed kimberlite often exposed in eroded gullies or cutbanks. Though sticky and visually nondescript, it's often studded with small black grains, ilmenite, chromite, and red to purple garnet fragments. If found in a slope, break, or natural trench, it warrants sampling. Lamprate, on the other hand, is rarer but no less significant. The world's most productive colored diamond mine, Argyle in Australia, originated in a lamprate pipe. Unlike kimberlite, lamprate is richer in potassium and may contain feldspar, mica, often phlogopite, and serpentine. It's typically brown to greenish in weathered form, often friable and associated with volcanic breccias. You may notice a soapy texture in hand samples or flakes of mica glinting in fine matrix. Field indicators of lamprate include unusually soft, chalky rock zones, sometimes interbedded with pyroclastic textures, evidence of volatile-rich eruptions. Like kimberlite, it often weathers to clay-rich soils that form circular vegetative anomalies. Look for isolated knolls, patches of unconsolidated material, or sites where coarse fragments sit atop degraded slopes. In both rock types, xenoliths, fragments of deep mantle rock like peridotite or eclogite, are a critical find. These pieces are carried upward intact and sometimes contain microscopic diamonds or inclusions of the same minerals that hint at the parent conditions. If you break a cobble and see greenish granular textures or dense black spinel crystals, collect it. Even without a visible diamond, the rock's chemistry can justify lab assays. Another surface clue is carbonate veining or alteration. Kimberlites often emit Co2-rich fluids during emplacement, leaving white carbonate streaks or nodules in adjacent rock. These veins may resemble calcite or dolomite and tend to weather quickly, but their association with magnetite and serpentine sets them apart. A magnet sweep in such areas may show dispersed ilmenite or magnetite fragments embedded in decomposed matrix. Paired with panning results downstream, this provides a breadcrumb trail back to the vent. And if you find both indicator minerals and host rock fragments in the same zone, especially within 100 meters, It's time to initiate a high-density sampling pattern and consider bulk material collection. For every promising exposure or rich concentrate, there's a real-world hazard waiting nearby, often unmarked, fast-moving, and indifferent to how close you are to a major discovery. Field safety in diamond prospecting isn't optional, it's foundational. Whether you're working creek beds, hill slopes, or remote gravel fans, your ability to manage terrain, weather, and wildlife can determine not just your success, but your survival. Water first. Most diamond indicators concentrate in or near active or ancient drainages, which means you're often working inside or adjacent to seasonal flood zones. In regions with rapid runoff, like highlands or desert arroyos, rains upstream can cause sudden flow surges, even under blue skies. Always check the catchment area above your site. Avoid narrow canyons or bedrock traps when skies are unstable. If you're working a paleo channel, ensure it hasn't reactivated due to nearby development or upstream redirection. Place your gear above waterline and always have an escape route, especially if you're working solo. Dry bags for sample logs, labeled concentrates, and test kits are essential. Many discoveries have been lost to a single slipped pack or unanticipated flash rise. A lightweight but rugged dry sack should be considered as vital as your pan. Slope stability is next. Kimberlite and lamprite pipes often lie in eroded depressions or at the base of weathered hills. These areas can suffer from loose scree, collapsing soil, or undermined roots. Before descending a slope to collect, test the surface for cohesion. Use a walking stick or geological hammer to probe ahead. If sampling near an undercut bank or gully head, stay clear of overhangs, especially in zones of clay or decomposed rock, which can slump under weight or vibration. Vegetation clues and hazards go hand in hand. Dense undergrowth often masks sinkholes, wet spots, or unstable terrain. Conversely, healthy vegetative rings can indicate fertile kimberlitic soils, but may also be home to territorial wildlife. In parts of North America, South Africa, or Australia, this includes venomous snakes, feral pigs, or large cats. Always step deliberately, keep a first aid kit accessible, and avoid working near dusk or dawn in known wildlife corridors. Legal access matters as much as physical safety. Sampling on private land, tribal territory, or restricted zones, even unknowingly, can void any future claim, invite fines, or lead to equipment confiscation. Always consult national or regional mineral rights databases, and if possible, contact local landowners before entering. Some of the most promising indicator trails in underexplored regions lie on land leased for grazing or forest use, areas where courtesy, transparency, and sometimes written permission go a long way. Not every glittering sample deserves the cost of formal analysis. With assay prices often ranging from $50 to $300 per stone or concentrate, the question of when to escalate to a lab isn't just logistical, it's strategic. Knowing when your field evidence reaches the threshold for lab validation is what separates deliberate prospectors from those who burn resources on premature signals. That decision hinges on one hard rule: repeatability. A single promising grain, no matter how brilliant under UV, how dense in water, or how adamantine its luster, is never enough. Diamonds are rarely found alone. Their eruptions were explosive and mineral-rich, meaning that even eroded systems should leave behind multiple traces if a pipe is nearby. That's why the decision to spend on a lab must rest on grid-confirmed patterns, not isolated anomalies. If 3 adjacent sample sites, spaced 25-50 meters apart, each yield garnet plus chromite ilmenite, with at least 2 grains per pan per mineral, you've crossed the first threshold. This suggests transport from a common source and warrants escalation. Conversely, if the same indicator appears in only 1 out of 10 sites, you're likely chasing drift or noise. When a suspect grain exhibits multiple positive tests, non-magnetic, high SG, UV active thermal conducting, and others in the same grid do too, your confidence increases. Look for consistent properties across multiple grains, not just one high performer. Lab-worthy samples should come from geologically valid terrain. If your grid lies within mapped kimberlitic or lamproitic domains, especially near historical pipes, suspected intrusions, or old float zones, that context strengthens your case. Submit only when sample behavior and terrain logic align. Many labs prefer bulk samples, 10-20 kg, of heavy mineral concentrates over single stones. If your grid yields 5-10 grams of promising non-magnetic heavy minerals from multiple sites, this justifies a multi-grain assay, where labs extract and analyze microinclusions or mineral chemistry for signs of mantle derivation. Before sending samples, clean and catalog them properly. Use acetone or ultrasonic cleaning to remove surface contaminants. Store in labeled, tamper-proof containers with detailed site logs, GPS coordinates, elevation, sampling depth, grid position, and field test results. Labs prioritize well-documented submissions and often reject samples without context. Not all diamonds are created or priced equally. Once you confirm that your suspect stone is, in fact, a diamond, the next pivot is immediate, from identification to valuation. Because what determines whether your rough is a novelty, a cutting candidate, or a commercial-grade asset isn't just its existence, it's a tight matrix of factors: carat weight, clarity, color, morphology, and origin. Each of these interlocks to define how and if your find fits into the market. Start with size, the most direct driver. Rough diamonds under 0.2 carats, 40 mg, are typically valued by the parcel, not individually. Their worth is determined more by aggregate color and clarity than by individual characteristics. Between 0.2 and 0.5 carats, stones begin to gain identity, but still only marginally. A 1-carat rough diamond, if clean and clear, marks the threshold where individualized valuation truly begins. Larger than that, and even imperfect stones can fetch premium pricing, if they cut efficiently. But size is nothing without clarity. Inclusions reduce value dramatically. In the rough, internal fractures, cloudiness, or foreign mineral inclusions can drop the potential cutting yield or force inefficient cuts. Stones with high clarity in rough, transparent, with limited internal markings, are far rarer and can command 2-3x multiples over similarly sized, flawed rough. Color cuts both ways. Colorless stones are the standard, but some hues, especially natural pink, blue, or intense yellow, can push prices far higher, depending on origin. However, gray, brown, or black tinges typically reduce value, unless they're associated with specific high-interest sources like argyle or Golconda. A slight tint in a 0.5 CT stone might have its price. That same tint in a 5 CT could cost tens of thousands in lost premium. Morphology matters too. Octahedral rough, with flat faces and minimal surface breakage, is easier and more efficient to cut. Flattened or irregular stones may have good carat weight but poor yield, leading to a lower valuation. Stones with frosted or abraded surfaces are less likely to produce brilliant faceted gems without deep cutting, which reduces the final size and the price significantly. Then comes origin, a subtler but growing influence in diamond valuation. Stones from known ethical sources, Canada, Botswana, Namibia, often command a 5-15% premium in select markets, especially when traceable to specific mines or certified by third parties, e.g., GIA Origin Reports, Canadamark, Tracker by De Beers. Conversely, untraceable rough from artisanal contexts or undocumented sources may be discounted, even if quality is high, due to compliance risk for downstream buyers. The leap from field find to financial reward is the most dangerous phase of the process, not because the stone will vanish, but because its value can. Many independent prospectors, even after identifying a legitimate diamond, walk away with a fraction of what it's worth due to missteps in verification, insecure handling, or trusting the wrong buyer too early. Diamond fraud doesn't always involve fakes. It often involves real stones priced as if they were. The first trap is undervaluation by substitution. In less formal settings, field offices, backroom labs, or casual buyers, there's risk that your stone may be swapped for a lower-grade lookalike during inspection. The original returns to you altered, and the buyer now holds the real gem, pretending otherwise. Always photograph your stone under magnification from multiple angles before submitting it. Note unique internal inclusions, edge features, or polishing marks. High-resolution macro images serve as a digital fingerprint, useful for dispute or confirmation. The second is misclassification fraud. An unscrupulous buyer may claim your rough is industrial grade due to surface frost, small inclusions, or minor tints. These defects may exist, but still fall within commercial or even premium cutting tolerance. Without a trained eye or certified lab report, you're vulnerable to being offered 10–30% of true market value under the guise of expert opinion. Always seek third-party confirmation, ideally from an independent lab or gemologist unaffiliated with the buyer. Third is mislabeling during certification. In some jurisdictions, lightly regulated certifiers may misidentify stone origin, downgrade clarity, or classify a natural diamond as treated or synthetic, permanently affecting resale value. To avoid this, work only with established institutions. GIA, IGI, HRD Antwerp, or Gubelin for colored diamonds. These labs provide digital tracking and tamper-proof submission methods. For Canadian stones, SRC or Canadamark provide both provenance and technical validation. There's also delayed or withheld payment. Some dealers, especially those operating internationally, may accept the stone, promising payment upon resale or after lab grading, then vanish, reclassify the stone under a shell entity, or dispute its origin. To protect against this, use conditional consignment agreements, held in escrow through legal or gemological intermediaries. If the deal involves export, ensure your stone's paperwork complies with Kimberley Process Certification Scheme, KPCS, standards to avoid seizure or reclassification at borders. Fake interest offers are another tactic. A buyer may show excitement, pressure you to act fast, and even offer upfront cash only to later claim the stone failed testing. These are often ploys to either spook you into selling lower or force a return at a loss to you. Resist urgency. Let the test speak. At some point, speculation ends. The stone in your hand or the grains in your vial must either cross the final threshold into verified diamond or fall just short. This last stage, used by gem labs, advanced field teams, and professional buyers, is not about probability. It's about eliminating ambiguity using a layered suite of tests that converge on a single conclusion. And each test reveals something distinct: origin, composition, behavior, or market potential. Begin with UV fluorescence under controlled lighting. This is no longer your handheld flashlight in a tent. In a lab, long wave, 365 nm, UV is applied in a dark chamber, allowing comparison to known diamond standards. Most natural diamonds fluoresce pale blue, some show yellow or orange, and a few, especially from Argyle, exhibit strong pink or violet. But just as important is the stone's phosphorescence, whether the glow persists after the light is off. Most natural diamonds don't. Moissanite and some synthetics do. A clean, consistent, non-persistent blue glow is a positive sign. Next comes thermal conductivity, this time with precision probes. Lab-grade testers quantify heat dissipation rate, not just pass-fail signals. A true diamond shows a steep drop in temperature under probe pressure, far beyond quartz, zircon, or spinel. Moissanite may still match, but this is where the electrical conductivity test completes the picture. Diamonds are insulating, moissanite semiconductive. If your candidate conducts both heat and blocks electricity, the field score tightens toward diamond. Then the optical suite. Using a refractometer, your stone's refractive index, RI, is measured. Diamond's RI is 2.417 with virtually no deviation. Moissanite sits around 2.65–2. 69, but double refraction distorts this reading. Under crossed polarizers or fiber optic lighting, birefringence becomes visible, the key differentiator. Facet lines in moissanite double or blur under magnification. In diamond, they stay sharp. If you've got a polished crystal face, Even if it's small, this test often resolves the last doubts. Specific gravity is confirmed through precision water displacement, balancing dry weight versus submerged weight to 2 decimal places. A diamond lands at 351-353. Any significant deviation up or down suggests alternate material. Heavy fakes like zircon 4-6-4-7 and spinel 3-6 will not match. When combined with RI and thermal data, the match becomes statistically firm. Spectroscopy closes the case. Advanced labs run Raman spectroscopy or infrared absorption, FTIR, to detect lattice structures and trace elements. Diamonds exhibit a unique spectral fingerprint, sharp peaks at 1332 cm in Raman, and clear nitrogen-related absorption bands in FTIR. These tests also help determine whether the diamond is natural, HPHT synthetic, or CVD grown. For colored diamonds, photoluminescence helps isolate natural versus irradiated color causes. And finally, microprobe or semi-DS testing of accompanying indicator grains can validate the stone's likely origin. If your garnet sample shows G10 chemistry, low calcium, high chromium, or if your ilmenite contains the T-Fe ratio typical of diamondiferous pipes, you've not just found a diamond, you've proven it came from a likely economic source. Once the diamond is confirmed, the question is no longer if it holds value, it's how that value will be realized. At this moment, the prospector faces a fork in the road. Sell the stone as rough, cut it for maximum yield, or partner with others to develop the claim behind it. Each path leads to a different outcome, shaped by risk tolerance, long-term goals, and the nature of the discovery itself. Selling the rough stone is the most immediate route to cash. For many, it's the obvious next step. But the rough market, while active, is built on conservative pricing. Buyers expect to profit from uncertainty, so they discount heavily for flaws they might find during cutting. Even a well-formed 1.2 carat rough, confirmed as natural diamond, might fetch only $2,000-$3,000 if sold directly. Without documentation, no lab report, no origin details, the offer might drop further. This is where certification pays. A verified report from a recognized institution like GIA, IGI, or SRC not only authenticates the stone, but raises buyer confidence, often increasing value by 20% or more. Cutting the stone opens the door to higher margins, but it also brings new risk. Most rough loses nearly half its weight in the cutting process. That same 1.2 carat stone might yield a 0.5 or 0.6 carat polished gem, depending on clarity and shape. Cutting costs can run from a few hundred to over $1,000, especially if grading, laser inscription, or custom faceting is involved. And once cut, the stone enters a slower, more selective market. Now it must compete not just on size, but on brilliance, color, and presentation. Still, for stones with exceptional clarity or rare hue, pinks, blues, intense yellows, the payoff of a successful cut can multiply the original value several times over.